In this lesson, we're going to start to finish graph two rational functions. Rational functions have a really wide range of what they can look like. So I actually highly recommend that you go experiment a little bit with graphing some different kinds of rational functions on Desmos. All it has to do to be a rational function is have a polynomial in the numerator and a polynomial in the denominator. And then you can get a taste for how just wide the variety of shapes you'll get in these graphs really truly is. Okay, so when we're going to graph fully a rational function, the first thing we're going to do, let's take our first example. Graph f of x equals x squared plus 6x plus 5 over x squared minus 3x minus 4. So we're going to try to get a sense of what this thing looks like. So the first thing to do is we want to be able to easily identify vertical asymptotes, x-intercepts, and such. So the first thing we're going to do is, if we can factor the polynomial, if it's not factored already, we're going to try to factor it. Okay? So we're going to factor, and we are going to get, in the top we get x plus 1 times x plus 5, because those multiply to 5, add to 6. In the bottom we get x plus 1 and x minus 4. Now in this polynomial, the polynomial is in the top and the bottom. We actually see something we haven't seen before. We have this situation right here where we have the same factor in the top and bottom. So can we just cross it out? Well, let's think about this for a minute. So x plus 1 and x plus 1 are always the same. That's for sure. X plus 1 divided by x plus 1, what does that equal? Well, x plus 1 divided by x plus 1 equals 1, except where x equals minus 1. Okay, where x equals minus 1, we get 0 over 0, and we don't actually know what 0 over 0 is. We usually call that indeterminate. Okay, so this is equal to 1 except where x equals minus 1. Okay, so what we're going to do is we're just going to kind of put that in our pocket for a second. I am going to cross these two terms out and just say we will revisit at the point x equals minus 1. And one thing we know for sure is that x equals minus 1 is not in our domain. Is not in the domain of the function. Okay, so once we've got that little bit cleared up, we're going to come back to x equals minus 1 when we're graphing and talk about what that is. We are going to start by finding the function's vertical asymptote. So let's draw a graph. This is going to be where we will put the graph of our function. Now I'm just going to shrink this a little bit so we can get everything in the window and see all the information we're going to be working with here. Okay, so our vertical asymptote well, if I look at the denominator, we have x minus 4, and that can't be 0, so our vertical asymptote occurs at x equals 4. Horizontal asymptote, well, I have x plus 5 over x minus 4, so that's going to be a big number over big number equals 1, or you can use the rule from the book where you divide the coefficients of the highest degree term if they're the same. So our horizontal asymptote y equals 1 is our horizontal asymptote. Okay, so let's look at our y-intercept. Well, if I plug in x equals 0, I get 0, negative 5/4 is our y-intercept. Okay, how do I do that? Well, it's because 0 plus 5 over 0 plus 4, sorry, 0 minus 4 is going to give us that negative 5/4. We replace x with 4. For our x-intercept, well, we see in the numerator, the only thing that's going to make the numerator is 0. We're going to look at x plus 5 equals 0. So we're going to have an x-intercept just at negative 5 comma 0. And finally, let's take a look at what do we think is happening at x equals minus 1. Okay, so what we're going to call at x equals minus 1, we have a canceled factor which causes a point or a removable, what we call a point or removable discontinuity. So a discontinuity is just anything in the function where you have a little bit of a jump, or the function stops existing for a minute, where it's not continuous and you can keep drawing. Essentially, a function is continuous if you can draw it without having to lift your pencil. At the point you lift your pencil, the function is no longer continuous. So what does that mean? Basically, it means that for every point other than minus 1, we can ignore it. At the point minus 1, what we're going to do to find our value is we're going to plug minus 1 into what's left, because this is what the function is approaching as we get closer to minus 1. But at minus 1, the function just stops existing just for that little moment. So we want to know where the function is going when we're going towards minus 1. So as we get really close to minus 1, we get minus 1. So as x approaches minus 1, we get minus 1 plus, we are approaching minus 1, y is going to be approaching minus 1 plus 5 over minus 1 minus 4, which gives us a negative 4 on top and a negative 5 on the bottom, which gives us a positive 4/5. Oh, sorry, a positive 4 on top, negative 5 on bottom. So that gives us a negative 4/5. Let's get those signs correct. So what this means is we are going to have a, quote, the way we draw it is we just draw a little hole in the graph. The technical word is point or removable discontinuity. But hole is what we can use in conversation. And that's also what it looks like when you draw it into the graph. That is going to be at negative 1 comma 4/5. Okay, so the next thing, so what we're going to do is we're going to take all the information that we've collected about the features of this particular rational function. We're going to put in our vertical asymptote at x equals 4. You can see I'm not doing a super crazy accurate graph. There's no need to do that. We'll put in our horizontal asymptote at y equals 1. This will give us a reference place right here. Okay. We will put in our x-intercept at negative 5, and we can put in our y-intercept at negative 5/4. Sorry, this should be a negative 4/5. Let me keep my signs everywhere correct. Okay. So we'll put that just below, if this is negative 1, negative 5/4 is just below that. Okay. So now we're going to play with our rational function, connect the dots. Here are the rules. Well, we can stay, we're not allowed to cross either of the axes except at an intercept. So we know that this right here has to go something like that. Okay, and we cross the axis here, and then we're going to head up for 1. And we know as we go over here, we're going to go down because there's no other x-intercept, so we can't go back up before we get to that vertical asymptote. At the vertical asymptote is like a wall. So when you hit the vertical asymptote, you have to either go down, 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 or up, 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 up in an asymptotic way. So you're approaching the vertical asymptote but never arriving at it. So if I kind of want to see how quickly this is happening, this is where making a table comes in. So I don't recommend that you make a table for every single x coordinate. You don't have to go like, oh, negative 5, so I'll do from negative 5 to like positive 6 and do 11 points. That's not necessary. What we want to do is we want to make a table anywhere where we're not quite sure what the graph looks like. So what I might do, so just so I have another dot to connect, is I might pick x equals 3. And then to calculate y, I'm going to do 3 plus 5 is 8, 3 minus 4 is negative 1. So at 3, I'm already down at negative 8, which is going to be somewhere down here. So that gives me a sense of kind of how steeply my graph is bending down. And then I can draw that arrow because I have my asymptote, so I need to be taking off for infinity. So y is negative 8. Okay, so this is called, I call this a strategic table, because it is something where we are only plugging in the points that we need to. Okay, so let's try maybe on the other side. So now I'm not sure exactly whether I'm going to be coming back up from the bottom or coming down from the top. So I'm going to plug in 6 and see where I am. So if I plug in 6, I get 6 plus 5 is 11. And then 6 minus 4 is 2, so 11 over 2 is 5.5. So it looks like I'm going to be coming down from the top. So even at 6, I'm still only right here. So I'm going to be going up this way, and then kind of slowly making my way down this way to go out with my horizontal asymptote. And it may take me a while before I get really close to my horizontal asymptote. Now, one thing we skipped, we had our hole. So I really recommend you draw these graphs in pencil, because then you can go back and just erase and put the hole in where you need to. So at negative 1, right about there, negative 5/4, we need to put a little hole in our graph. And essentially what you do is you just draw an open circle and then continue the graph on both sides around that open circle. So that open circle represents the little missing piece, that point discontinuity, where the function just stopped existing for a minute because it canceled out everywhere except at that one point. We don't quite know what it did. Okay, so let's just summarize what are the steps. So step 1, okay, is, okay, we find our vertical asymptote and domain. Step 2, we find our horizontal asymptotes. Just our one, generally these will only have one horizontal asymptote. Remember, you can cross through the horizontal asymptote. You can only cross the x-axis at an x-intercept. So we're going to find the x and y intercepts. And then once you've got all of these things plugged in, to help you in your little game of connect the dots, you are going to make a strategic table of values. When you were graphing with a table of values before, often you were making something of a strategic. So if you were trying to graph a parabola, you might make a table of values, but you would have to make sure that the vertex was included in your table of values, so you really saw that point that it turned around. So this is something similar, except I'm not asking you to put in quite as many points. I just want you, if you don't know what the graph is doing, pick a point in that area, plug it in, take the y value, and that's what the graph is doing right there. Okay. Let's do one more example of graphing a rational function. And in these two examples, I'm trying to give you a range of what your function might look like. However, there are so many different ways they can look. So really checking it out on Desmos will give you a sense of what are kind of reasonable things for a rational function to come out looking like. So we're going to graph this rational function, y equals x minus 2, x plus 4, x plus 5, x squared times x minus 1, x plus 2. So we're going to ask that we graph and summarize features. Okay, so let's draw in a nice ready graph. Be prepared to even, I think I've just grown how big I'm doing things, so maybe even zoom out just a little bit again. And so let's start. We don't have to do any factoring, so we know vertical asymptotes. Well, it looks like we have, sorry, this this one up top, I've copied it wrong from my notes. This should be an x minus 1. Okay, so I'm going to go ahead and cancel this x minus 1, but I'm going to write in the domain as well. Okay, so my vertical asymptotes are the ones where the bottom is 0 but not the top. So I have a vertical asymptote at x equals 0, and I have a vertical asymptote at x equals minus 2. Those make the denominator 0, but my domain is x not equal to 0, also positive 1, and negative 2. Okay, so the point 1 is excluded from my domain, but this is going to be a point discontinuity. Okay, so for the rest of my work, I'm going to try to use just what I have left and not worry about the point discontinuity except what I'm drawing in the graph. So my horizontal asymptote, well, in the top, and when you have things that are already factored, you have to expand. Think about what the highest power of x would be when it would be expanded. So we have like an x squared in the top because we have an x times x, and we have an x squared times x, which would give us x to the third. So since the highest power is in the bottom, we're going to have a horizontal asymptote at y equals 0. Okay, next let's look at the x-intercepts. What makes the top 0. So we have an x-intercept at negative 4, 0, and negative 5, 0. And again, remember how I've said a couple times, I think, that you can cross the horizontal asymptote. This is evidence. We have a horizontal asymptote at y equals 0, but we have 2 points that actually intersect that horizontal asymptote at some point. Vertical asymptotes, they're walls, you can't cross them. Okay, and finally our y-intercept. Well, we actually don't need to go looking for a y-intercept because x equals 0 is not in our domain. So we have no y-intercept because there is a vertical asymptote there. Okay, so we have a point discontinuity, and that happens at x equals 1. So I'm going to plug it into what's left. I get 1 plus 4, 1 times 1 plus 5 over 1 squared times 3. So that is 5 times 6 is 30. So the point discontinuity is at 1, 10. Let me just checking my math in my head. Okay, lovely. So now I'm going to plug these things in. I'm going to start plugging them into my graph. So I have here, and I'm actually going to make, like, because I know I have to get up to 10, I'm going to make this 5 and then 10 on my negative 5, negative 10. Just make my y-axis a little bit more expanded just so we can get stuff in. Then we have sort of 1, 2, 3, 4, 5, 1, 2, 3, 4. Okay, so I have a vertical asymptote at x equals 0, and then I have a vertical asymptote here. Okay, so that's kind of tight. Then I have a horizontal asymptote here on the x-axis. I know that I cross the x-axis at 1, 2, 3, negative 4, and then also at negative 5. So it looks like I'm going to go either up and back down or down and back up. And I have a point discontinuity at x equals positive 1 and positive 10. So I know that right here is a point discontinuity. Okay, so now I'm pretty sure because of my point discontinuity that this one is coming down from above. But I'm going to check and just see how fast. So let's start making a strategic table because otherwise I don't really know exactly whether we're on top or on bottom. So let's try maybe like, I kind of want to know what's happening at negative 4.5 because that's between my two intercepts. And if I know whether we're going up and coming back down or down and coming back up, that's going to be helpful. So if I get negative 4.5, I plug it in and I get 0.0049. So it's a really small positive right here. Like it's like you can barely see it coming up above the x-axis. So this would tell me that this goes back down. If it's up here, it's going to go back down below here because we're not squaring the term. So the root has to be, we're not squaring it, so it's not going to go back up and back down. And then we're going to go down here. And I'm actually going to see, I kind of want to know how fast that's happening, so I'm going to plug in -3, and at -3 I get -0.2. That's actually not really very much movement, so that's going to be like still almost like right at the x-axis. So let me try -2.5. I want to see if it started to really curve down by then. -2.5, I get -1.2. So that's going down a little bit faster, but it's still right here. So you can see that that kind of goes down really, really sharply and close to this asymptote. And sometimes it does it. So it's good to have a few points just to see what's going on. So now I have no idea what's going on between my two asymptotes, so I'm going to plug in -1. Kind of a halfway point is usually good. And I get 12. So if I'm here at 12, how do I know if I go up or down? Well, here you can use your asymptotes to tell you what's going on. If I'm coming from here and I'm going this way, if I go down, I would have to cross the x-axis. So I'm going to assume that this goes up. Might it go down and then back up? Sure, but I don't need to get it to that degree of detail. I just want to have a sense of what the general shape of the graph is. And here, if I at 1, -1, if I'm going towards 0, the same problem. If I were to go down, then I would have to cross the x-axis so that I can head to -infinity with my asymptote. So instead, I'm pretty surely heading up to +infinity in this asymptote. Sometimes they do really, really weird things on a small scale, but I'm not concerned about you knowing exactly which points you should plug in to make that happen. That's more what you'll do in calculus. When we have a few more tools we can use to figure out what's going on. Okay, so now we are going to look at, we've got our hole, and then we are going to plug in, let's plug in 2 just to see how quickly that's coming down. I plug in 2, get +2.6, so that's going to be by 2, I'm going to be all the way down there. So it looks like I'm going to be heading for my asymptote relatively quickly. Still not going to get there, but that's what the graph of my function is going to look like. Okay, is it perfect? Probably not, but it gives me an idea of the general shape, and you can graph it on Desmos to see exactly what you do. So just to run through one more time our steps: vertical asymptotes and domain. Start with that, vertical asymptotes and domain, horizontal asymptotes, x-intercepts and y-intercepts, and point discontinuities you can plug in at this point, and then also do your strategic table of values just so that you know what's going on.